Hello. So we have been recording videos on techniques for solving or determining velocities of points or particles with an emphasis on rigid body kinematics. So let us just specify our objective. So our objective is to show techniques for finding velocities of points / particles, and our emphasis is on rigid body kinematics. So emphasis on rigid body kinematics. Okay, and so what we are going to do today is we are going to demonstrate technique 2, which is determining velocities using relative velocity relations. Okay, so that's going to be our objective, and we are going to revisit the same problem that we had taken in the previous video, which was that let us consider a cylinder or a disc which is moving on a horizontal surface, and let's say the horizontal direction is x, capital X, vertical direction is capital Y, and the direction perpendicular to the surface of this page pointing up outwards is Z, and let's say that this is our origin and this is a fixed reference frame, and here is a disk with a center at C. Let's say that there is a point P whose velocity we are interested in, and let's say that at an arbitrary instant it has made an angle theta with respect to the vertical drawn through the point C, and its angular velocity is theta dot. Okay, and the location of the center along the x-axis is small x. So just to keep in mind, we are not really specifying whether the cylinder is rolling without slipping, or so we are not necessarily specifying that. We can impose that condition later, and we will make some observations in regards to that proceeding forward. But for now, let us assume that the center is at an arbitrary distance x, and the rotational speed is theta dot. And so there are two different coordinates that are needed to completely specify the orientation and location of this disk, and that is x and theta. Okay, now the technique that we are going to demonstrate, so keep in mind that in the previous video our goal was to find the velocity of the point P using direct differentiation of its position. So what we did is we took the position vector of the point P and then we differentiated to find the velocity, and we showed some of the nuances. We showed that you need to set up the position vector properly. Otherwise you would have errors in finding the velocities, especially when you are trying to find the velocity of the point P at a certain orientation or at a certain location, specific location. So in this video, as we have said, we are going to use directly the relative velocity relation. So instead of going from position and differentiating to get the velocity, we will directly use relative velocities. Now the idea of relative velocities is a pretty fundamental idea. In fact, it comes from the idea of relative vectors of one point with respect to another. And so for instance, if we say that let's say this is our x, y, z coordinate frame, and this is a fixed coordinate frame, and let's say that there are 2 points, point A and point B. Let's say that the position of A is RA and position of B is RB. These are the two vectors, and the position and the vector going from A to B is RB with respect to A. Then you can say that RB with respect to A is equal to RB minus RA. Or in other words, you can also say that RB, the position of the point B, is equal to RA, the position of point A, plus RB with respect to A. So in other words, if you want to reach B, what you can do is you can draw a vector to A, and then from A you can draw a vector to B, and then the sum of these two vectors is going to be the position vector of the point B. This is a very fundamental relation in relating positions of any 2 points in space. And if we then carry out a differentiation, so differentiation, then we get the relative velocity equation, which says that velocity of B is equal to velocity of A plus velocity of B with respect to A. All we have done here is we have differentiated this equation with respect to time, and we have this relation. So this relation can be directly used. So this relative velocity relation, so this is our basic relative velocity relation, and this relation can be used directly in finding velocities of points when you are dealing with problems in kinematics. So let me just quickly check what I wanted to say here. Now we need to understand that this approach of using the relative velocity relations directly is useful. So the relative velocity relation, and let's call this equation 1, is useful for determining VB if VA is known or easy to determine, and VB with respect to A is also known or easy to determine, right? So if we can obviously use this equation to find VB, let's say in a given problem we are interested to find the velocity of a point B, we can use this relation if we can spot a point A whose velocity is easy to determine, easy to formulate, and relative to that point A there is this velocity of B relative to A, which is also easy to spot, or which is also easy to formulate, okay, or it may be known. So if such a scenario happens, then it makes sense to try using this relative velocity relation. Now, this relative velocity being easy to determine is, in many cases, this is easy if the points B and A are on the same rigid body. So if B and A are on the same rigid body, then often we find that there is a specific formulation of the velocity of B with respect to A. Note that here, when we have given these relations, we have not imposed anything on the points A and B. A and B could be any points or any particles. What we are saying is, if A and B are on the same rigid body, there are certain simplifications that can help us in determining this velocity of B with respect to A. So let us look into that aspect a little bit. I forgot to put one parameter here. The distance between C and P, I put it in the last problem. It is D. So D is the distance between C and P. Okay. Now, going back to our relative velocity expressions. So we note the following, that let's say, and for the sake of simplicity, let's just restrict our discussion to 2 degrees of freedom, but or rather 2 dimensions, but we don't really have to restrict ourselves that way, but this is just for the sake of simplicity. So let's say we have X, Y and Z. The circle with the cross indicates that the y-axis is directed into the surface of the page. So X, Y, Z forms a right-handed vector. Now let us say that there is a rigid body here in space, and let's say that there are 2 points P and Q on the same rigid body. Now let's say that the rigid body moves, and perhaps it moves in a curved path, but as it moves, it does not rotate. Okay, so it does not rotate, meaning that as you track the point Q and you track the point P, you find that this line P to Q has the same orientation as the rigid body moves. So maybe I can draw a slightly better picture. So imagine that the rigid body moves like this. Here is the original location, and here is the final location. This is P, this is Q, and this is P, and this is Q. Okay, so this line from P to Q remains parallel at all times as the rigid body goes from one instant, as it goes from its location at one instant to a location at a different instant. This kind of motion is called a curvilinear motion. So here, rigid body takes a curved path. However, no rotation of the rigid body. Okay, so it does not have any rotation about its axis or about perpendicular to its axis, or there is absolutely no rotation. So any 2 points, if you identify any 2 points on the rigid body, P and Q, and if you track the motion of the rigid body, then what will happen is that for any 2 points you will see that the line P to Q will always remain parallel to itself as the motion of the rigid body happens. Okay, so there is no rotation, but the rigid body takes a curved path, and it does not have to be a curved path. I mean, the curved path is just a special or a generalization of a linear motion. Okay, so the rigid body could also take a linear motion. So this kind of motion is called a curvilinear motion. It is not a motion where the rigid body has a rotation. Okay, so there is no rotation involved, but the rigid body has a curvilinear path. This is very similar to a particle just following a curved path. Okay, this motion of a rigid body is very similar to a particle following a curved path. So in this case, what happens is that so here Q and P have no relative velocity with respect to each other. So there is no relative velocity between P and Q with respect to each other. So in this case, VQ with respect to P is equal to 0, and P with respect to Q is of course also equal to 0. Now note here that VQ with respect to P is equal to the negative of VP with respect to Q. Okay, because it's just a vector which is opposite in direction of the other one. So Q with respect to P is this vector. So this is VQ with respect to P. Okay, and P with respect to Q is going to be the vector going from Q towards P. Okay, so neither of these two will have any non-zero quantities because the rigid body is not rotating. And we deliberately talk about curvilinear motion because we want to clarify that just because a rigid body is rotating in a path, in a curved path, does not mean that the rigid body has a rotation. And if the rigid body does not have a rotation, then any 2 points on the rigid body will not have a relative velocity with respect to each other. Okay. Now, when will then the 2 points on a rigid body have a velocity with respect to each other? So Q and P will have a relative velocity with respect to each other. Actually, I shouldn't say will. I should probably say may, because there are a few exceptions when the 2 points on the rigid body are on the axis of rotation, okay, or parallel to the are such that they are parallel to the axis of rotation. Even then, there is a case where the velocities of the relative velocity of Q and P may be 0. But there is a possibility that Q and P will have a relative velocity with respect to each other only when the rigid body has an absolute angular velocity, and we can call that angular velocity omega. So when a rigid body has an absolute angular velocity, and we say absolute angular velocity just to differentiate this angular velocity from any relative angular velocities. Okay, so if the rigid body within an inertial reference frame, okay, has an angular velocity, then there is the possibility that Q and P, which are 2 points on the same rigid body, can have an angular velocity with respect to each other. So for instance, now if we say that, going back to that same example, let's say this is x, this is z, this is y, this is a fixed reference frame, and here is the rigid body with p and q like this, and then the motion of the rigid body happens such that q goes here, p goes here, and this is the new orientation of the rigid body, or new location and orientation of the rigid body. Now we see that the orientation of this line from P to Q or Q to P has changed. Okay, if Q to P is this vector, or sorry, P to Q is this vector, and now P to Q is this vector, we see clearly that the vector has changed in its orientation. And so this under this condition, you do have a relative velocity of q with respect to p, and that velocity is given by v, let's see, q with respect to p is equal to the angular velocity of the rigid body cross product with r q with respect to p. So what is this rq with respect to p? That's this vector. So let me just say that rq with respect to p is the position vector of q with respect to p. So this is the relation of the relative velocity of q with respect to p, and it is given by omega cross r q with respect to p. Now you can see right away from this equation that first of all, if there has to be a relative velocity of one point on a rigid body with respect to another point, you need to have an angular velocity. Without an angular velocity, and this is the absolute angular velocity of the rigid body, which means that, let's say the rigid body has rotations along or that can be resolved along multiple axes, let's say x and y, then the angular velocity omega is the net angular velocity. Okay, it's the net angular velocity vector of this rigid body. So that cross rq with respect to p is the velocity of q with respect to p. Now just because an angular velocity causes this this cross product to be possible does not mean that if the rigid body has got an angular velocity, there will necessarily be a relative velocity of q with respect to p, right? Because you can have an angular velocity, but p and q could be the same point. Of course, then it doesn't matter. There is no relative velocity. The other possibility is, since this is a cross product, when is this cross product? When is a cross product equal to 0? Well, a cross product is equal to 0 if these two are along the same direction. So for instance, if the rigid body has got an angular velocity in a certain direction and q to p is also in that same direction, or it's parallel, then omega cross r qp is not going to be, q with respect to p is not going to be any non-zero number. It's in fact going to be 0. So in fact that tells us that if I take a rigid body and if q and p are on a line that is parallel to the axis of rotation, even then, although the rigid body is turning, there is not going to be any relative velocity between q and p. Okay, so you have to look also at mathematically as to under what conditions this cross product will be non-zero, and those would be the conditions where you would get a relative velocity of q with respect to p. Okay, so however, this is a pretty fundamental relation, and this relation can be used when we try to find out the velocity of a point on a rigid body with respect to another, and this relation will be particularly useful in this problem that we are solving. So let's go to the next page and let's now revisit our problem and try to solve it using this relative velocity idea. Okay, so if I take that idea, then I can say, just a second, then I can say that Vp is equal to Vc plus Vp with respect to C. This is the basic relation, relative velocity relation that we mentioned at the beginning of this discussion. And now we have, so this is the basic relative velocity relation. And as we are writing this equation here, this equation is valid no matter what the points P and C are. Okay. Now, if P and C are on the same rigid body, as is this case, right? In this problem, you have that scenario where the points P and C are on the same rigid body. Then we have additionally Vp with respect to C is omega cross Rp with respect to C. Right? And so now we can say that therefore Vp is equal to Vc plus omega cross Rp with respect to C. Okay? Now, now let us consider the point C, right? Note that the point C, if you track this point C as the cylinder moves, what you will notice is that the point C follows a straight line path, because the point C is the center of this cylinder, and as the cylinder moves on this horizontal plane, the point C will just move along this straight line path. Okay, and in fact the location of the point C is x, so we can directly say that Vc is nothing but x dot I. I mean, you can take the position and differentiate, but it's quite obvious from an understanding of the physical motion of this cylinder that Vc is going to be x dot, and it's going to be in the direction of the x-axis. Now let us try to figure out omega. Omega is the net angular velocity of this rigid body, and the angular velocity of this rigid body is theta dot. Why is it theta dot? Because theta represents the position of P with respect to C, and that position, the angular position rather, and the position or the orientation rather, and the orientation is measured with respect to an inertial, a fixed direction. So since it's being measured with respect to a fixed direction, meaning the vertical direction here, then the angle that P is forming with respect to C is also an absolute angle, because this direction is not changing, and with respect to that unchanging direction you are measuring this angle theta. So theta is an absolute angle, and theta dot is the angular velocity. And to find the direction of the vector of the angular velocity, what we do is we use the right hand rule. We curl our fingers in the direction, so in the direction of theta, okay, and the thumb then represents the orientation or the direction of the vector. So the thumb is pointing inwards into the surface of the page, and so that is negative z direction, so minus theta dot k is the angular velocity. Now what is Rp with respect to C? Rp with respect to C is the position vector P with respect to C, and so this is the vector going from C towards P. Okay, so first of all its magnitude is d, that's the distance between C and P, and let us determine the individual x and y coordinates. So the vector goes from C to P. Okay, so in other words, if I sketch it here, so P is here, C is here, this is my vertical through the center. Just for reference, this is my x-axis, the horizontal direction, and this is my y-axis, the vertical direction is the y-axis. This is theta, and so we are interested in the vector going from C to P. So if we draw a horizontal here, and if we extend this line, we notice that RP with respect to C is d times the distance d times cosine theta points it in the j direction, and plus sine theta resolves it in the I direction. Okay, so what I mean, keep in mind that what you can do is draw a perpendicular line from the point P to the horizontal, so that will form a right angle triangle, and then treat this PC as the hypotenuse, and then the adjacent side and the opposite side distances are basically the x and y distances of this vector. So rewriting that over here, cosine theta j plus sine theta I. Okay, and so this is our angular, this is the position of P with respect to C. So now let us carry out this cross product. So therefore VP is equal to VC, which is x dot I, minus theta dot K cross d cosine theta j plus sine theta I. Now we need to do a cross product. When I do these cross products, I typically use a graphical way to remember how these cross products are going to work out. Note over here that if x is the horizontal, y is pointing towards the vertical, then a right-handed rule gives me z to be going out of the page perpendicular to the page. And so if you this I have found to be a nice way to remember the cross products. I make a graphic like this. What this graphic tells me is that if I do I cross j, I'm going to get k. If I do j cross k, I will get I. Okay, and if I do k cross I, I'm going to get j. On the other hand, if I do I cross k, then I have to go in this direction. So I cross k is going to give me j, but negative j because I'm going in the reverse direction. Okay, so keeping that in mind, then I have x dot I minus theta dot d cosine theta times k cross j minus theta dot d sine theta times k cross I, which is x dot I minus, now k cross j is basically going from k to j in the opposite direction as the positive direction considered. Now this positive direction is basically my positive, the direction in which, the direction that I use to set up my right-handed coordinate frame. My right-handed coordinate frame is such that if I curl my fingers from I to j, I will get k. Similarly, if I curl my fingers from j to k, I'm going to get I. And if I curl my fingers from k to I, I'm going to get the direction j. So that is how the right-handed coordinate frame is described. So that is what is replicated over here. So it gives us directly the method to carry out these cross products. When I do k cross j, I go in the opposite direction. So k cross j is going to give me I, but it's going to give me negative I because I'm going the opposite direction. So then I'm going to get plus theta dot d cosine theta I. and k cross I need to go in the same direction as the positive direction. So k cross I is going to give me j, but a positive j. So I'll have negative theta dot d sine theta j, and so my result, the velocity of the point P is x dot plus theta dot d cosine theta I minus theta dot d sine theta j. And you can verify that indeed this is the velocity that we got by using the direct differentiation of the position vector of the point P. And so we have shown that the relative velocity approach is another valid approach for finding velocities of 2 points. It is particularly useful when the 2 points are on the same rigid body. There were two basic results that we pointed out. The first result is that for any 2 points in space, you can relate the velocities of those 2 points using this relation, that is velocity of B is equal to velocity of A plus velocity of B with respect to A. And this comes from the direct differentiation of the position. The position of B is equal to position of A plus position of B with respect to A. That was one relation. The other relation that we have used is the fact that when the 2 points are on the same rigid body, let's say 2 points P and Q, then the velocity of Q with respect to P is given by the angular velocity of the rigid body cross product with the position of Q with respect to P. Okay, so these two have been used in finding the velocity of the point P in this problem. The point P and C were on the same rigid body. C is the center, and we used the fact that the velocity of C is rather easy to find, and that's because C is the center and it moves along a straight line, and based on the orientation and location of the disk, the velocity of the center is easy to quantify. It is x dot I. So that's what we have done over here. And because P and C are on the same rigid body, indeed the velocity of P with respect to C is omega cross R with respect to R of P with respect to C. Omega was easy to quantify because we have a pretty good understanding of the angular. It's actually given the angular position, and so negative theta dot k was the angular velocity. P with respect to C, the position, that is, was also easy to resolve. So we were able to rather easily determine these two vectors, carry out the cross product. In carrying out the cross product, what we did is that we used the fact that we are using a right-handed coordinate system, and in a right-handed coordinate system, the definition of the coordinates, the way the coordinates are oriented, they themselves lend to how the cross products take place between the different unit vectors. And so we use that to find out the cross product when we do the omega cross R, and from there we found out the velocity. So that's the end of this video, and what we are going to do next is we are going to make some observations regarding the velocity of different points on this disk, and we are going to also show what happens to the velocities when we impose a rolling without slipping. It'll give us the idea of the instantaneous center. And next we will also look into some ideas of rotating coordinate frames, and so those are videos that are upcoming. So thank you for watching, and let me know if you have any comments or suggestions. Thank you.